Hello, good evening, sir. Lipo Wang, sir. Shall we start the session, sir? Hello.
Okay,
Shall we
yeah.
start the session now?
So I
Okay,
should
sir.
start.
Yes, sir. Good evening to all, and it is my immense pleasure to welcome you all to the fourth day of the AICT sponsored ATAL 6-day online faculty development program on transforming industries with AI, deep learning breakthroughs, and real world applications, organized by the Department of Computer Science and Engineering, SRM Institute of Science and Technology, Ramapuram, Chennai. It is my privilege to welcome our esteemed resource person for day 4, the session 7 of this faculty development program, Dr. Lipo Wang. We are honored to introduce Dr. Lipo Wang, an associate professor in the School of Electrical and Electronic Engineering at Nanyang Technological University, Singapore. Dr. Lipo Wang earned his bachelor degree from the National University of Defense Technology in China and his PhD from Louisiana State University in the USA. With over 19 years of experience, his research focuses on artificial intelligence and machine learning applications in communications, image and video processing, biomedical engineering, and data mining. He has authored over 320 papers, including 110 journal articles, and holds a US patent in neural networks. Dr. Lipo Wang has also written two monographs, edited 20 books, and his work has been cited approximately 7,800 times according to Google Scholar. Throughout his distinguished career, Dr. Lipo Wang has been a keynote speaker at 40 international conferences and has served as an associate editor and editorial board member for 30 international journals, including 4 IEEE transactions. He has also been a guest editor for 10 journal special issues. His leadership roles include serving on the board of governors of the International Neural Network Society from the year 2011 to 2016 and IEEE Computational Intelligence Society from 2010 to 2015 and IEEE Biometrics Council. He was Vice President for Technical Activities of the IEEE Computational Intelligence Society and Chair of its Emergent Technologies Technical Committee, as well as Chair of the Education Committee of IEEE Engineering in Medicine and Biology Society. Dr. Wang also served as President of the Asia Pacific Neural Network Assembly, receiving its Excellent Service Award, and was the founding chair of both IEEE Engineering in Medicine and Biology Society Singapore chapter and IEEE Computational Intelligence Society Singapore chapter. Dr. Liu Wang's distinguished career, including over 400 publications and recognition among the world top 2% scientists by Stanford University, underscores his significant contribution to the field. In the day 4 session 7 of our FDP, Dr. Lipo Wang will present on deep learning for time series data classification and prediction. We will cover application in electrical power systems and healthcare, sharing his extensive expertise in this domain. Kindly join me in extending a warm welcome to Dr. Lipo Wang to our faculty development program and invite him to share his insights and inspire us with his words. Welcome you, sir.
Thank you so much, Dr. Sudha. I need to share my screen. It
Yes,
doesn't allow
yes,
me
sir.
to
I'll
share.
make this. Wait. Now you can share your screen.
Okay.
Oh.
Okay. Thank you. Yeah. Okay. You can see my slides.
Yes, sir.
All right. Oh, okay. How come it disappeared? Okay. Let me try again.
Screen is visible, sir. You have to put slideshow, sir. No?
Yeah. I need to move away this one. This bar is blocking my view. Okay.
Yes, sir. Okay, sir. Fine.
Okay, great. Yeah, okay. Thank you, Dr. Suda, for giving me the opportunity to share the research with you. So the title of my talk today is Machine Learning for Time Series Data Processing. Okay, so the application would I'm going to talk about include EEG recognition, which can be used for emotion recognition, stress monitoring, fatigue detection. And next, I'm going to talk about application to partial discharge detection in power systems. Then I'm going to talk about application to video processing. So video is a special time sequence because it's a sequence of images. I'm going to talk about, in particular, uh, person re-identification and action recognition in video. Then I'm going to briefly talk about stock trading and prediction. So this is another special case of time series prediction. So in the case of EEG processing, EEG is the electroencephalograph. It's very hard to pronounce. So it's a brain wave. Okay, so you put electrodes on the skull, and then you can measure the wave at each point. So so you can see that each of these spots is considered as a channel. Okay, so one electrode at each place can measure the brain wave, such as this. So one electrode will measure a time sequence of the brain wave, and this is another electrode. So we can measure a whole bunch of different channels on the skull, and then we can analyze all these time sequences collectively. This EEG is can be used for many applications. In the medical domain, we can use it for diagnosis of various conditions. One of the condition is attention deficit hyperactivity disorder, ADHD. So so this is a very good way of investigating ADHD in children, for example. And we can also use it for diagnosis and prediction of epileptic seizures in patients. And it can do many other disease that's related to the brain. In addition, we can use EEG for human-computer interface. For example, if for some handicapped people, they don't have a control by the hand. Some people handicapped, they don't have a hand, or the hand has lost the mobility, and they would use their brainwave to control computer. For example, they can control computer. They can through a computer. They can also control other things. And also, for example, when people are busy with their hands, for example, the doctors in the operating room, the hands are busy with the operation, but the doctor would have to communicate with the computer sometimes, for example, to pull up a patient record or do something, control the computer. They can use this EEG to do something, to control the computer. In the area of neuromarketing, we can monitor the EEG of customers. Then we can really know what the customers think. Whether they like the product or they don't like the product. Sometimes they cannot express properly with the speech, or sometimes they just don't want to tell you how you think about the product. So you, from the EEG, you can actually tell what they really like the product or not. In neural feedback training or serious games, you can use EEG to do many things. Yeah, for example, you could train some people uh, to control the emotion. For example, some people gets very emotional, and then you can use some kind of therapy. You can try to recognize the emotion, and then use some kind of therapy to control, to help the patient control their emotion, help the people to control their emotion. And also you can monitor the stress of people. Some people are doing their work, and sometimes they get very stressed. And if you monitor it continuously, you can make sure that they don't get overstressed. If they're stressed out, some things may happen, and it's endanger their personal safety. So that is something you're trying to avoid. So you can use EEG to monitor people's stress. So you can try to recognize stress, and then when the stress level gets high, and then you do something to reduce the stress level. You can train people to concentrate or relax depending on the need. Okay, for example, athlete. If you're training a athlete for Olympia, and then you want them to concentrate properly, and some people have trouble concentrating. You can try to get them. You monitor their concentration, and then you try to get some feedback and help them to concentrate. And some people are really tense. So sometimes you help them to relax. Okay, so you can monitor their brain activities, and see if they're too tense. And when they're too tense, you try to, for example, play some music, and do something to get them to relax. So this help some people. And also it can also help people, train people for multitasking. Yeah. We sometimes we try to do a few things at the same time, and you can try to help them. You help them to multitask. Um, Sometimes these are called serious games. So it's not, if you're playing computer games in normal sense, it's just for fun, right? But if you can make some serious games. Serious games means that the game is designed to train people to do something. Okay, for example, to uh, to get people to relax, and to get people concentrate, and to get people perform better with multitasking. So this kind of games is called serious games, and people have designed some serious game, and my students have done that as well, and they design some serious game to help train people, okay, to accomplish a certain task, or to perform better in certain task. Okay, so I'm going to discuss some of these things in detail. And the first thing I'm going to discuss is emotion recognition. Okay, so this is what we normally do, and some of my students are doing these things, and you can see that what do we so in the experiment, what we do is we want to collect some EEG data. So how do we do this? We usually have to give the subject, we need to get some volunteer to volunteer their time, and they sit down in the lab, and and let the student to measure their EEG when they do something. For example, if we're going to uh, if we're going to monitor the emotion, and we sometimes show them uh, to present them with some kind of music, some kind of music. It could be very sad music or something, or it could be very happy music. The purpose is to induce the proper emotion that we're looking for. Okay, so and sometimes you could show them an image. So the image could be very sad, or the image could be very happy, depending on the thing you want to try to the kind of emotion you're trying to induce. So you can show them different images, and you can also show them different videos to induce the proper emotion. Okay, and this is the sort of the setup. And then what we do is we try to measure the EEG. So the EEG device we use is called emotive. Okay, so this is sort of the new kind of device. And previously, previously you can see that these are the older uh, measuring devices. So you can see that you put it on their skull, and then sometimes you have to inject some gel into each of these electrodes to increase the contact ability between the electrode and the skull. So you can get better signal this way. So this is sort of the older way of measuring EEG. But the newer way of measuring EEG, we usually use the dry electrode. So you just put it on, and there is no need to have a messy these liquid to inject. Okay, so these are the things that we're using now. Then you can induce different emotions using these things, pleasant, happy, frightened, or angry, different kinds of emotions. So here we induce four kinds of emotions, and then we're going to try to train a machine learning system to recognize these things. Okay, so we can once we get to the EEG recorded. Like I said before, the EEGs are looking like this. So the EEG are waves looking like this and this and this. Uh, you can feed this in a neural network to train the neural network to recognize a particular segment. For example, if you know this part of the EEG is a sad kind of emotion because you show the subject some sad video, and then you know this is sad, and then you train the neural network to recognize, to sort of memorize. Okay, this is the sad emotion, and then you train a few times, and the next time you show a piece of the EEG that you don't know whether it's sad or happy, you try to show the neural network, and then the neural network is supposed to recognize. Okay, it's supposed to recognize the emotion. So this you can feed in you can feed the raw data. That is these are the raw data. You can feed in the raw data and to the neural network. You can also do some feature extraction before you feed in the machine learning model. Um, so for example, you can extract band power of the signal. You can extract some kind of statistics from the signal. You can extract fractal dimension. So there are different mathematical formula to extract these features from signals, and you can just extract them. And then there are also higher order crossings. There is something called peak alpha uh, and also peak alpha frequency. There are also mutual information. There are also auto-regressive coefficient, etc. So there are many of these kind of features. Basically, these features are designed by people, and you can extract them. Sometimes they help to they help training the model to get a better recognition. Okay, so once you have these, you can use these, or you can use the raw data. Okay, and these are the input of to the machine learning model. Well, what are the machine learning model you
Aisha,
can use?
provide
Yes, somebody had a question or something? Okay. Okay, so you can train different machine learning models. So for example, this one, you can have many machine learning models. For example, this is called LSTM. It's a long short-term memory. It's and also you can train CNN, convolutional neural networks. So these two are deep learning models. And then you can use shallow machine learning models. There are many of those. So for example, there are support vector machines, there are artificial neural networks, k-nearest neighbor classifiers, and also there are linear discriminant analyses, and the hidden Markov chain, etc. There are many of these, probably hundreds. Okay, hundreds of these classifiers you can train with the data. Once you train them, and they can be used to recognize unknown signals. Okay, so you might say, well, how do you know which one to pick? Well, it's a very hard question. Yeah, so sometimes we just compare. We just pick a few and compare and choose the best one, because for different data, different model will perform the best. Okay, different. Uh, some people would ask, nowadays people use deep learning. Okay, people use deep learning such as LSTM, CNN. Yeah, people use this. So why do we bother with the shallow, the older machine learning models? Well, because the data. Okay, the deep learning models require huge amount of data. Okay, uh, for example, if you want to train a convolutional neural network to recognize some images, usually you're talking about millions or billions of images. Uh, for images, it's very easy to get so many images. However, for EEG data, it's very hard to get. It's very hard to get because the process involved is quite laborious. You have to, first of all, you have to get people to agree to come and let you measure the EEG. So that's the hard part. And yeah, nobody wants to spend the time and sit down and let you mess around with their brain. So you have to find people who are willing to let you measure, and then you have to sit them down and get them really quiet down with don't think too much in their brain, otherwise the thing will interfere. And then you have to show them some kind of emotion inducing videos or images, and then get them to the right mood. Okay, and then you can start measuring. Okay, so you can measure, but you measure a few minutes, and then probably they have to they you probably have to start over again, because you probably have to get them into the right mood again, because they might have forgotten what the video is about, and their brain is drifting off, and the signal is probably no longer sad or whatever you want to try to measure. So this is very hard to measure the data for EEG, very hard. So so normally my students can get probably 20 people to come into the lab and measure the signal. So 20, you're talking about 20, maybe 40, it's not a huge number. You cannot possibly get a 1 million data set. It's just impossible. Okay, there are some data sets that's available on the internet. It's also considered to be quite small comparing to image data set. Okay, so this is why, you know, sometimes these deep learning neural networks don't really work so well. Sometimes these classic neural networks works better because the data set is very small. Okay, so this is the problem with EEG processing. Okay, so this is I already talked about some of these, and there are different approaches. There are traditional approaches. Shallow model require pre-extracted features. That's a feature we talked about. Some power spectrum, some statistics, and so forth. And there are many of them. Okay, there are many of them. You know, it's very hard to know which one that is the best, and also it's very ad hoc. So in other words, you know, you just come up, you just dream up something, and then you do the calculation and you get the feature. Okay, it's very ad hoc. It's not very systematic. Then the features are human constructed and interpretable. So this is the sort of advantage. You know what the feature is about. You know, for example, the feature is about power spectrum. Okay, and then you know it's about power at different frequencies. Um, you know, so it's interpretable, but not sure if they fully reflect the characteristic of the signal, you know, because you know you extract a few features. What about the rest? You could in principle come up with millions of such features, but you cannot do 1 million features. You probably could do 20, 30 features. That's it. Then you're not sure whether these features are fully reflecting the characteristic of signal. Okay, so in other words, if you only do these features, you may lose out on the information in the EEG. Okay, so uh, uh, in contrast with traditional method, you can also do deep learning. Deep learning is to learn features by training. In other words, you just feed in the raw data. You don't extract features. Yeah, in principle, you don't have to, but some people still extract features for deep learning. Yeah, so people do different things, you know, just try different things. So in principle, you can learn features by training from the raw data. However, the problem, as I said, is a small data set compared to images. We're going to, for example, we have 20 subjects, about 30 channels. Yeah, for each subject, you can have channels, different channels on the scale, and but these numbers are still very small compared to millions of images, you know, required for deep learning. Okay, so another problem with EEG is that there is a huge variations across different subjects. You know, for example, if you measure the same signal, for example, if you measure the sad emotion, you measure the sad emotion for different people, right? And then you measure the signal, and then you okay, and then you take the signal, and then you try to analyze the signal, for example, by principal component analysis. So these are the basically one way to analyze. You can analyze it in many different ways. So this is the principal component two, principal component one. So suppose you have measured many people, like here we got 28 people. So suppose you have measured their sadness of emotion, and then you display these signals in this graph in terms of the principal component, and then you can see that it varies a lot from people to people. Okay, so you know, for example, this is one person, with the sad emotion, and then this is another person with the same sad emotion. So you can see that, although it's also the same emotion, but from different people, and the signal looks totally different. uh, if you have this kind of situation, how can you train the machine learning model? Okay, so what we did is we try to do some kind of a domain adaptation, basically trying to massage the signal from different people to make them more similar to each other. Okay, so you can see this is the original signal, and then you do some domain adaptation, or sometimes we call it the transfer learning, because we basically we want to transfer diff information or knowledge from different people into the same domain. You can see this is subject one, subject two. You got this subject. A different subject will have different signal, and then you try to massage them into the similar. They make sure they look the similar. Okay, look similar, and then it's easier to classify if the signals are very similar. Okay, so you can see that this is what's happening. This is what's happening. So this is the old signal. This is the old signal. You can see that they're all different, very different from different people. They're very different, spread out or different. But now if you do this transfer learning, and they become very similar. They are all clustered in the same place, and they all look very similar. So this way, this way you can train the machine learning model better using the this new signal. Okay, so this is another data set. You can see that before you do the transfer learning, the different people would have different different signals. Different color will have different places that shows up uh, for different people. They're different color, and the signals look very different. Everybody has their own place. But if you do the transfer learning, so they are more similar with each other, and then you can train the thing much better. Okay, so you can see here, it's uh, it's the result. It's the result. Um, you can see here we have different ways of different methods. Okay, different method, and then you do the domain adaptation or transfer learning. Then you can see that you can uh, increase the accuracy. You can increase the accuracy, right? So this is for example, you can transfer the knowledge from this to this. This is different. This is different data set. This is one data set. This is another data set, and you can transfer the knowledge between data set, and then you can increase the accuracy. Okay, so the next thing we did is to recognize fatigue. So in the as you know, when people drive their car, and sometimes they get fatigued if they drive a long time without proper rest. Okay, so it's quite dangerous when people are drowsy, and then they doze off, and then this accident will happen because he dozed off and he lost control, and he just lost control. He just lost the he doesn't see anything. So the accident will happen very quickly. And so what you want to do is we want to have a system to recognize this kind of a fatigue, driver fatigue. Okay, so for example, you could do it with EEG. So for example, you let this person drive, and then you measure the EEG from this person. All right, and then you can see you can try to find out whether the person is drowsy or not, is fatigued or not. Okay, so so how do you know the person is fatigued? Well, you can what you can do is you can let you can drive. Okay, you can let the person drive. For example, if a person is not fatigued, and usually he would drive in a sort of a straight line, right? If the road is straight, and he's supposed to be driving in a straight line. However, if the person is fatigued, he may just lose it. He may just lose it. He may deviate. He may deviate from the direction that he's supposed to go. And then, for example, he just doze off here, and then he's just wandering around, and he comes out here, and then he suddenly realized that wow, he made a mistake. He correct his mistake. He will come back there in the same place. Okay, so this thing you can consider the person is really fatigued. Okay, already sleeping. Okay, so the person slept for 1 second and then wake up. Okay, so this is the thing. This is the thing we're trying to measure. So and the experiment is actually done by these group of researchers, and they have done this experiment, and they have measured the data, and they have kindly made the data available for everybody to use. So what happens is that they measure this kind of data, and then determines this is the fatigue area, and this is the EEG that corresponding to the fatigue area. Okay, and then uh, we will use different kind of machine learning model to learn this thing. This is a fatigued area. So before that happens, we call it baseline. Maybe maybe it's not fatigued, and this area is fatigued. Okay, and then this area, the person has come back and waken up. Okay, so the different areas, or different areas would have the different EEG signals, and then we use this information to train the machine learning model. Okay, so the way we trained it is that we used a EEG net. Okay, the EEG net is invented by some people. Basically, it's a CNN. It's a convolutional neural network. So they have done the CNN, and so the input basically it consists of these structure. So you have different layers in CNN. You got input and then convolution layer, and then this is called the batch normalization layer. And then you convolution again and batch normalization again, and then you just do this. You do a few times, and then before you train a classifier. So this is the normal CNN, and they call it these people call it the EEG net because they use it for the EEG recognition. Okay, so what do we do differently is this. In the batch normalization layer, what these people did is they will use just a single batch normalization layer for every subject, for everybody. For one subject, two subject, you got 20 subject. They use just a single layer for everybody, and this way, you don't handle the difference between the subjects well, because all the subjects are different, and you use just one layer to treat everybody, and the result may not be the optimal. So what we did is that we use what's called a subject dependent normalization layer. So you can see this is batch normalization layer for subject one. And then we train another batch normalization layer for subject two. Okay, and then if you have M subject, we train M different batch normalization layers. Okay, so this is during training. Well, what happens during testing? So, well, after you training, you get a few these normalization layers, and then what happens during training is that you try to find out which signal this incoming signal is most similar to. Okay, so suppose this incoming signal is most similar to subject M, and then you just use this batch normalization layer. You don't use these ones anymore. Okay, you just use this one. Okay, so this is what the my student did in this research, and he come up with this kind of thing, and then he trained the neural network, and the performance is better. And you find, okay, so here is his experiments, uh, and you can see that this is what we call a leave one subject out cross validation. So every time you train, you just leave one out, leave that subject out for testing. Okay, so this is what we call leave one subject out, and you use all the other subject for training. You can see that he tested this on different models. So this is the original EEG net with a single batch normalization layer. And then you have other models like deep learning network, SVM, and so forth. And then this is the subject matching model that he invented. And you can see that, well, for different subjects, there is accuracy. Okay, there is accuracy. And you can see that his model is not the best for every subject. Okay, for every subject, he's not the best. For example, for this subject, this model is the best, it's 90%, and his model is only 78%. And for this subject, subject one, as SVM is the best, 71%, and his accuracy is only 68%, right? Uh, and uh, uh, his result is the best for only for the fourth subject and only for the fifth subject. And well, you might say, okay, what's the big deal? I mean, his model doesn't even perform best for every subject. Well, but the power of this thing is that the average among all these accuracies for different people is the highest. You can see that the average for different model here is lower. Okay, is lower. Um, so his average is highest. Well, that's something. That's something. Uh, yeah. Another thing you want to pay attention here is that the accuracy is 74% on average. It's not very high because compared to the images, if you talk about image recognition, well, the accuracy can be as high as 99% or even 100%. But here is only 74%. Well, this is because the data is not a lot. Okay, like I said before, the number of data available is only 20, 20, 30, that kind of thing. And it's not very much. So if you can achieve this kind of accuracy, it's already something. Okay, it's already something. It's very difficult. Okay, another thing my student did is he trying to augment the data. Uh, like I said before, the data is not sufficient. So how do you solve that problem? Well, you can you can generate data. You can generate data. How do you generate data? Well, you can do various things to the data. For example, you can add noise to the data, to the data itself. You can add noise to the frequency domain. Okay, you can add noise. And here there is a way to do it is called time warp. So what you do is you just expand you just expand the signal, stretch the signal. Okay, so you can see that the the blue line is the original signal, uh, and then the red line is the generated signal. So what's the difference? Well, you just stretch the original signal to the new signal. Okay, so you stretch it a little bit. Uh, so you can do various stretching, and sometimes you stretch more, sometimes you stretch less, and then you come up with many different signals, and this way you can generate a lot of signals. This is called adaptation, data augmentation. Okay, signal augmentation. So we can do this. All right, so you can see that there are many things you can do. Okay, many things you can do. For example, you can do this. You can do frequency masking. Oh, what it means is this. This is the original signal, and this is the Fourier transform, the fast Fourier transform. That's a frequency domain. So what you do is you just cut out a part of the frequency. Okay, you cut out. Yeah, of course, you randomly cut out. Okay, there is no definite way how you decide which one to cut out, which frequency to cut out, how much frequency you cut out. Well, it's just random. Okay, you just cut out. For example, in here we just cut out this piece, and then we transfer this back to the time domain from the frequency domain, and then you get a new signal. Okay, so you get a whole bunch of new signals this way. So here is the frequency noise. So frequency noise, this is the original signal, and this is the frequency domain, and then you add noise to this frequency domain, and then you transfer the thing back to the original signal, and then you get a new signal. Okay, so there are different ways of generating a new signal. Okay, so well, which one works better? Which one works better? So we try different ways and see what happens. You can see that this is the frequency noise method, and this is the time warp method where we stretch the thing, stretch the signal, and this is the frequency masking method. Okay, well, my student just tried these three methods and see which one works better. Okay, so for subject dependent training, subject dependent means that you train a machine learning model for each subject, for each person. Okay, one person you train a model, different person you train another model, and of course different model would be used for that one particular person. This kind of thing usually works with a higher accuracy. For example, you can even achieve 91% accuracy, right? But this thing is trained with one person's data and used for that one person. Okay, so this is called the subject dependent data. And then you can see that if you combine for this kind of model, if you combine the time warp with frequency masking, so these two give you the best result for this kind of model. However, if you want to do subject independent training, in other words, you got 20 people, and then you use everybody's data to train one single model, okay? And then use that model to test on everybody. So obviously that's more challenging, okay? So this is called subject independent training, and the accuracy you expect is lower, okay? So what's the best way of what's the best way of data augmentation? Well, we tried everything. This one is without data augmentation. This one is with these two augmentation. This is you combine these two augmentation without this one. So a different combination. And for subject independent model, it turns out that you need all three. Basically, it's three different. In other words, you augment it as much as possible. Different ways of doing things, and you get the highest accuracy. Okay, so this is the conclusion he did. He reached. So for this one, for this one, he's comparing different frequency range and replacement with masking. So he did a lot of work. Okay, then my student did a lot of work using different data and different frequency and things. And this a different come up with a different result. Um, transform component. Okay, and so if you're interested, you're welcome to read the papers we published. They are all available on my website, and you can download and read my papers. If you are interested in the technical details, what kind of experiment we did, and what result we obtained. All these things are given in the paper in detail. Okay, so here I don't cover everything in detail. I'll just show you roughly what is done. So the finding is that data augmentation method help to correct the model on recognizing responsible things. Okay, so this is data augmentation, and this is the different ways of how do I see? I try to get rid of this bar. Oh no. Oh no, it's sorry about that. I tried to get rid of this Zoom bar. I wasn't able to do it. Let me just reshare the thing. Uh, uh, I'm sorry about that. Let me just reshare the thing. This one. Oh no, we quit and then share again. Uh, PowerPoint slideshow. Okay, share this one. Okay, so we're back. Okay, so okay, so here is more details about the data augmentation result. More details, and you can see that our result is highlighted here. Okay. 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 Okay, so here is the multimodal situation awareness. So there are multiple input. Okay, so it's given in this paper here. If you want to read the details, so what happens here is is you use different kind of data to do the you use different kind of data to do the training and the modeling. Okay, so okay, okay. So I let me talk about this one. So this is a neural network that my student used to train the signal, the EEG signal. It's called random vector functional link. So this is the model, RVFL, random vector functional link. This is a neural network model, and it consists of these things. It consists of an input layer and has an output layer, and then has a hidden layer. Okay, so you got the input from the output layer to the hidden layer, and then from the hidden layer you go to the output layer. So this is the connection. But in addition, there is a direct link, okay, from the input layer to the output layer. So you can see that there is a direct link here, all right? And so the output layer receives the signal directly from the input as well as from the hidden layer. So this is the interesting property of this RVFL neural network. Okay, uh, and okay, and then what? So this neural network was invented by some researcher, Paul. Okay, it's called his name is Paul. Okay, Pao. Uh, the year that was invented was 1994, I think 1992 or 1994, which is a long time ago. Okay, so you can see that this one is a shallow neural network, and it works quite well. Actually, it works quite well. And later on, recently, there's some other researcher invented the stacking, because they think this is the shallow neural network. And what they do is they just stack one after another. Okay, stack one after another, and you stack it multiple times, many times, and then you get a deep neural network. Okay, so for example, you stack it 8 or 9 times, it's considered to be a deep neural network already. Okay, uh, so what happens is this. Okay, so what happens uh, is this. So you can try, you can use different network to test the thing and see how they work. So you can see that you can compare different things with different models. So here is different methods, and here is the RVFL. S means stacking. Okay, means stacked neural network. Uh, and then you can see these are the other models. For example, here is called the SG Boost. This is the SVM. This is a linear regression. This is ICNN. Okay, and this is the EGNet. This is the deep network that we talked about before. Okay, so uh, you can see uh, you can see that there are different ways of doing things. Here we got another SG boost. This is this is the SG boost here, and this is the input with feature vectors cleaned EEG signal. Feature vectors, okay, and then the three is input with feature vectors eye tracking signal. Okay, so here we have the what we call a multimodal situation. We we not only have EEG signal, we also have eye tracking signal. Okay, eye tracking signal is measured from a special glass on the eye, and then you get to this, you get to the you get eye tracking signal. Okay, and and you can see that you can also do four. Four means input is feature vector EEG and eye tracking signal. Okay, so you can do EEG alone, you can do eye tracking signal alone, you can do both EEG and eye tracking signal. Okay, so here is the way to do it. Okay, there are different ways of doing it. And then you can use different data. Sorry, you can use different model to train the thing, and then you can see the result. Okay, again, this is for different subjects. We've got five subjects here, and then you can see that you got different result. So for this first subject, you can see that the best result you can get is with SG boost, uh, with only the EEG signal. Okay, so this is kind of interesting. This is with eye tracking signal. It's not the result. The accuracy is not as good. If you adding both eye tracking and EEG, the result is still not very good. I mean, the best is to just use EEG by itself. Okay, so but anyway, so the best result is here for the first subject, and for the second subject, the best result is obtained by using EEG net with only the EEG signal. without the eye tracking signal. Okay, this one is similar. You can also get the same result using SVM, using the using both EEG and eye tracking. Okay, so this is all very kind of random kind of combination. You know, so this one this one turns out the third subject turns out to be the best result is obtained by using the RVFL stacking uh, together with both EEG and eye tracking. Okay, so this is the third person, and the fourth person again is using EEG alone. This person, fifth person, is using linear regression stacking. Okay, well, you can see that every situation, everybody is different. So you might say, "Oh, what's the conclusion here?" Well, the conclusion is this: on average, okay, this RVFL stacking with both EEG and eye tracking gets the best average. Okay, so that's something very interesting. All right, there's something very interesting. Yeah. Uh, See, this is what's happening with EEG. You know, you got not so many data, and the conclusion is kind of all over the place. But fortunately, there is just one average that makes some sense. Okay, some makes sense. You know, by right, if you get more data, both EEG and eye tracking, you should work better. But it's not true for everybody. It's not true for everybody. But on average, this thing is better. And also, if you stack RVFL together, then this thing works better. Okay. Uh, with other stacking, usually it's still better. You know, you can see that if you stack them together with all the data, in general, the average is much better. It's better than all the stuff without stacking. Well, except this one, except this is 74.2, and you can see here we got 74.9. Okay, so this one is still both data, both eye tracking and EEG data. Okay, but this one is SG boost. It's not no stacking. Okay, so you can see that the result is kind of noisy. But yeah, but that's the best you can do with EEG signal. Okay, so this is the result. Here is some more information about this work. You know, you can do more about you can do more about this stacking of RVFL. You can see that uh, we have input, and then we have the hidden layer one, and then we have hidden layer two, and hidden layer so forth. So we just we get on and on. We got different hidden layers, and then we can have each hidden layer to the output. Okay, we have this hidden layer to the output and this hidden layer to the output, and all the hidden layer become output. So you can call this ensemble. Okay, you can call this ensemble, and then you get a final result. And this is this is kind of stacking. Okay, kind of stacking. So if you do this, you get a good result. You get the you get it's another way of stacking the thing up, and you get a good result. Okay, so this is raw, for example, raw data. You got piecewise convolution, and you got convolution and batch normalization, and then you get output RVFL. Okay, so this is you can consider these are the pre-processing. You use the neural network to do some pre-processing, and then you come out and do the classification. You use this stacking RVFL to do the classification. Okay, so it's a very convoluted method. You know, you combine CNN, you combine these different processing, and then you combine RVFL. It's a big combination, and if you do this, it turns out to work very good. You know, so it's kind of complicated and it turns out to be working quite well, right? So you can see that previously, yeah, this is the result from heating layer, okay, and then you get you get to the you get to a combination, and then you feed into the ensemble, okay, feed into the ensemble, and then you come up with a output, okay. So you can see here's the result. Here's the result. You compare with different models, and then you compare with SVM. This is random forest, and this is shallow CNN, and then EEG-net, and then this SM model, and then we have ICNN, and then we have ICNN plus RVFL, and then we have this big convoluted model that I just talked about. And you can see that for different, again, for different subject, well, the result could be different, but this model performs the best for subject 1, for subject 3, for subject 5, and for subject 9. Okay, so you can see that it does quite well. It does quite well. Okay, so the findings is this. This model, okay, this is also an RVFL model, but without all these convolution. Uh, with ICNN features substantially improve the SA recognition performance. You can see that this is, you know, if you compare this row with this row, it's much better. Okay, but you know, on average, this is much better than those. Okay, and then the proposed this big combination network is superior to the original model. Okay.
I have to say one last time, please. ఇప్పుడు కాల్ పని అమ్మవలసినదని சொன்னா and exactly I'm not telling about that. What do I do? I'm so confused. I did something stupid. I'm so sorry.
Don't say it. It's okay, Priya. It's okay. It's okay.
Can somebody mute? Can somebody mute that, please?
அவங்களுக்கு அந்த gas paying அதை தூக்கி எல்லாரும்
No, you are the host. Please mute some Madam Meena's.
ஃபேமிலி சொல்லிட்டு ஈவினிங் ஃப்ளைட்ல ரிட்டர்ன் ஆயிடும் சரியா
Yes, thank you, sir.
Okay. Yeah. So so this is bad. This is the best. Okay. So let me continue a little bit, and we're almost out of time. Let me just continue a bit. So you can we got different models to compare. So how do you compare with different models? With which one works the best? So what people do is they use different statistical ranking method to do the thing. Okay, to find out which one is better. You can see that all these numbers, they're kind of randomly distributed. Sometimes this is the best, sometimes this is best, and sometimes this is the best, and sometimes this is the best, and sometimes this is best. There is not a clear winner. Okay, there is not a clear winner. So how do you determine which model is the strongest? Which one is stronger? Okay, so there are actually statistical method to do it. Okay, so this is how it works. So first of all, we have this Wilcoxon test. So Wilcoxon test is a statistics between two models, So we're now comparing our big model, big complicated gigantic model with everybody else. So we do this what we call pairwise. We do, for example, we compare our gigantic model with SVM, and which one is better. And this Wilcoxon test will tell you, okay? It will tell you. You run the Wilcoxon test, it will tell you which one is better statistically, not absolutely, okay? Because we have concluded that nobody is an absolute winner. Sometimes this wins, sometimes that wins, but statistically, which one is the winner? Well, you can do pairwise comparison. So you compare this guy with SVM, and this guy is a winner, okay? And then you compare this guy with with random forest. This guy is a winner, okay? You compare this guy with the EEGNet, is again a winner. Basically, this guy beats everybody, okay? It beats everybody, beats shallow CNN, ICNN, SVM, ICNN, okay? Everybody is a beat. That means statistically, this one is better than everybody, okay? So this is what Wilcoxon test. Then you can use what's called a Friedman test as well. So what is the Friedman test? Well, Friedman test is a test between multiple things, and it will give you a rank. It will give you a rank, which one ranked highest, and which one ranked second, which one ranked the third. It will give you a rank, and you can see that this is the ranking. This is the ranking of each model. You can see that. Well, the ranking, the smaller the better. Okay, for example, somebody rank 1 is better than somebody rank 2, right? So, but statistically, nobody ranks 1 and nobody ranks 2, but these people rank a number. The ranking, there is a ranking number you can compute from a Friedman ranking. So you got these formulas. So you can see our paper to find out to find out how you do this Wilcoxon test and how do you do this Friedman ranking. There are definite formula. You can also Google these tests. Quite easy to do. And then this is the ranking number you obtain. Okay, so you can see that this guy actually ranked the top, and then this guy ranked the second. ICNN plus EDRVFL, it ranked the second. Okay, and then ICNN ranked the third. Random forest ranked the fourth. SVL ranked the fifth, and shallow CNN ranked 5, and then this one ranked the next. Okay, so you can see different things. Yeah, unfortunately, EEGNet ranked the last. Okay, so this is quite unfortunate because EEGNet is quite famous. Yeah, but unfortunately, our result indicate that it ranks last, behind the SVN, behind random forest, which are the shallow networks. This is a deep network. Okay. Well, again, that's just to show that the data is very small, but with this small data, our model works very good. Our two models, the big one ranked the best, and the smaller model ranked the second. Okay, both of these are RBFL models. Okay, so you can see that these are the findings. Based on the Wilcox model, statistical improvement achieved. Based on the Friedman ranking, the proposed had the best ranking. Okay, so that's the basically I think that's all I want to say for today. I run out of time, and I was going to say a few words. Maybe I just show you briefly what we did for this partial discharge recognition. So basically we did the project for the power company. the power company, they got these power lines, and they have transformers in the power line, and then they sometimes they got this discharge, which is not good. So this is okay. This is okay, but this is not okay. This means leaks. There are some leaks in the equipment. So this is called partial discharge. So we want to recognize this partial discharge so that people can fix the problem. So this is what we do. We build a model using LSTM to recognize the partial discharge. Okay, so you can see that these are the details, and basically our accuracy is very high. You know, it's very high compared to other models. And this is some more work about the same thing. You know, we will try to recognize the discharge. So you can see that this is an improved result. It's a 95% accuracy. Okay, so quite good. And this is our work with the stock prediction, and you can see that if you try to predict the price and then do the trading, you know when to sell and when to buy, and then you can make money. So this is our simulated. These are the simulated profit. Okay, so you can see that highest profit is obtained using what we have is genetic algorithm optimized support vector machine. Okay, so we have done this. Yeah, so basically there are other things we did is video processing. We try to identify the person when you know when the when in a frame when two person cross and then one person gets occluded, and then how do you identify that person back? So that's a person re-identification, and we did some work there. Yeah, so I don't have time to cover everything, but you can welcome to download all these papers. I got all the papers in my webpage, and you can download for free, and you can read about it. Okay, this is the work with action recognition. Okay, so you can see that there are different actions in video. For example, this is interacting with computer, a different video segment, and this is photographing, people doing photographing, and this is play music. So what happens if you want to retrieve a particular video? For example, you are interested in people riding bicycles, and then you can try to retrieve from the video. All the video is a huge database, and then how do you retrieve these things? So you can use machine learning to retrieve the desired segment of videos. Okay, yeah, so thank you very much. That's all I want to say. So if you have any questions, you can ask.
Dear participants, you are welcome to ask questions to Dr. Lipo Wang sir, who is prepared to address them. Kindly ask the questions one at a time. Participants, dear participants, you are welcome to ask questions to Dr. Lipo Wang sir.
Yeah, I got a question from this chat.
Chat.
It asks, most of these EEG data are stored in subject-based folders. How do we read the data for training purposes, and it is read individually? Yeah, so basically for each data, for example, depending on your training one model for one subject, or you're training the whole thing, you're training one model for the whole data. So depending on what you want to do, Suppose you want to train the one model for the whole data set for everybody, then you can just divide the subject into training and testing part. For example, you have one person for testing, and you get 19% for training. So you use the 19% data for training and the last person for testing. So you read this data individually up. Yeah. So that's how you could do it. Yeah. Okay. Thank you. Thank you. That's
Any more questions? Shall we conclude this session? And this marks the end of day 4, session 7 of this faculty development program. On behalf of Department of Computer Science Engineering, SRM Institute of Science and Technology, Ramapuram, Chennai, the organizing team of AICT sponsor ATAL 6-day online faculty development program on transforming industries with AI, deep learning breakthroughs, and real-world application. It is my privilege to extend a heartfelt vote of thanks to our distinguished speaker, Dr. Lipo Wang sir, for his enlightening session on machine learning for time series data processing and applications in medical diagnosis, electrical power, and video processing. Dr. Wang's extensive expertise in artificial intelligence, machine learning, and deep learning has provided us with a valuable insight into the practical application of these technologies in critical sectors. We are privileged to have benefited from this knowledge during this session, sir. Dr. Lipovang's session has undoubtedly enriched our understanding and will inspire us to further explore the transformative potential of machine learning in various industries. I also extend my great gratitude to all the participants for their active involvement and support in making this session a success. Thank you, sir. And all the participants are stay connected for the next session to be handled by Mr. Srinivas Tota, Senior Vice President, Kumaran Systems, Chennai. Thank you. Thank you, Unda. Thank you so much, sir.
okay. Thank you. Thank you. Okay. Bye bye.
Bye. Thank you. Thank you. Thank you, sir. So make me as a host and leave the session, sir. Thank you, sir.